Welcome to California's Great America, and today we will be giving a presentation on the one and only Demon! Now, when people spend the day at California's Great America, they go to experience the thrill of the rides, not to learn about how the rides work. Most people couldn't care less about the mathematical calculations and physics concepts that make their rides possible, as long as they are convinced the ride is safe and not deadly. Well, today we'll be giving you a highly detailed preview for the ride Demon, so that you won't miss out on any of the thrill.
Disclaimer. When we say highly detailed preview for the ride, we are including all the math and physics stuff. Warning, if the video will be ruining the thrill of the ride and possibly boring you to death. Do not watch and do not care about anything except the ride itself.
Today, I'm going to teach you guys about all the physics involved in this roller coaster, Demon. In physics, work is defined as FD cosine theta, where F is the applied force on the object and D is the displacement of the object in your system. In other words, work is the energy transferred to an object by an external force that is applied in the direction of the displacement. Work can also be used to remove energy from a system if the work is negative. This is when the applied external force is in the opposite direction of the displacement and motion of the object in your system. As we're being pulled up this ramp, work is being done on the carts. In turn, as the carts move up, this work is transferred to gravitational potential energy, which is the energy an object has due to its position in the gravitational field. Let's look at this concept visually with the help of an energy bar graph. On the left side, we have the work being done on the carts by the conveyor belt, and as the carts move up, the work is converted into gravitational potential energy, shown on the right. Thus, the total work done on the carts is equal to the gravitational potential energy at the top of the hill. This concept is known as the conservation of energy, where energy cannot be created nor destroyed, only transferred from one form to another.
Here, we can calculate the gravitational potential energy using the formula U sub g equals mgh, where m is the mass, g is gravity, or 9.8 meters per second squared, and h is the height of the object. At the top of the hill, the gravitational potential energy is at a maximum because the cart is at the maximum height of 30.3 meters. Thus, we can calculate the gravitational potential energy by substituting the known values into mgh, which equals 2.15 times 10 to the 5th joules. A joule is a measurement of energy in standard units. As soon as the cart starts down the hill, gravitational potential energy converts into kinetic energy because of the conservation of energy. As the cart starts losing potential energy and gaining kinetic energy, the cart accelerates and thus gains velocity. Velocity is speed with direction. It is a vector quantity. Kinetic energy is calculated by half mv squared, where m is the mass of the cart and v is the velocity of the cart. In order to find velocity at the bottom of the hill, we need to set potential energy equal to kinetic energy. mgh equals half mv squared. Since mass cancels out, we are left with gh equals half v squared, and the equation can be rearranged to be v equals the square root of 2gh. After substituting all of the values in, we get 24.37 meters per second. Here, we can use energy principles to determine the velocity at the top of the elliptical loop, which is called a clothoid loop. Objects do not undergo uniform circular motion in clothoid loops because the radius of clothoid loops is not constant. As the cart goes up the loop, conservation of energy suggests that the increase in height and the increase in gravitational potential energy results in the decrease of kinetic energy and speed. Thus, the cart has the greatest speeds at the bottom of the loop when both entering and leaving, and the lowest speeds at the top of the loop. Using this, we can calculate the velocity of the cart using conservation of energy. The gravitational potential energy of the first hill is equal to the kinetic energy and gravitational energy at the top of the clothoid loop. Solving for v, we find that the velocity at the top of the clothoid is 11.46 meters per second, which is indeed less than at the bottom. For the second loop, the same calculations can be made with the same method using the conservation of energy. When the cart enters the corkscrews, it undergoes uniform circular motion. Uniform circular motion is when the motion of the object is a circle at constant speed. The speed is the same at all points within the loop, but the velocity is different because it is constantly changing direction. As the object moves tangent to the circle, the velocity vector is also directed tangent to the circle. The cart, in this case, is accelerating as its velocity vector is changing in direction. Thus, there is a net force directed towards the center of the circle as F equals ma, in the same direction as the acceleration. This force is called the centripetal force. Because the inward net force is perpendicular to the velocity vector, the object is constantly changing its direction and undergoing inward acceleration. We can calculate the acceleration with the equation a sub c equals v squared over r, where v is the velocity of the cart and r is the radius of the loop. After substituting all of the values in, we calculate the acceleration to be equal to 111.32 meters per second squared. Since force equals ma, the centripetal force is just F equals mv squared over r. In order to calculate the centripetal force, we can multiply the acceleration by the mass of the cart, 80,707.64 newtons. At the bottom of the corkscrew, the cart would experience a normal force from the track, pointing up, and a force of gravity pulling it down. In this instance, the centripetal force, equal to the summation of forces, is the normal force minus the force of gravity. On the other hand, at the top of the loop, the cart experiences a normal force pointing downwards, in addition to the downwards force of gravity. These two forces added together is the centripetal force. Therefore, the normal force at the top of the loop is much less than at the bottom of the loop, making the rider experience a weightless sensation. Here, we have a banked turn. When the cart is on a banked turn, its normal force, that is perpendicular to the track surface, is no longer completely vertical and has a horizontal component. This horizontal force component becomes the centripetal force. The cart needs a specific velocity in order to round the curve successfully, and this velocity can be solved for by the equation v equals the square root of rg tan theta.
At the end of every single roller coaster to ever exist, the ride has to slow down to a complete stop before you can exit the ride. At the end of the Demon, the ride stops very abruptly. Using the formulas of kinematics, we can calculate the deceleration of the carts. The most fundamental equation in kinematics is v equals v naught plus at. Since the cart comes to a complete stop, the final velocity will be 0 meters per second. The time it takes the cart to completely stop is 1.46 seconds. The initial velocity, as calculated through the conservation of energy, is 24.37 meters per second. Using the formula, we calculated the acceleration to be negative 16.69 meters per second squared.
At the very end of the ride, we stopped abruptly with a deceleration of 16.69 meters per second squared. Without the handy-dandy lap bars and seatbelts, everyone during this 1.46 second interval would be ejected from their carts and die. This is inertia, otherwise known as Newton's first law of physics, which states that objects in motion tend to stay in motion, and objects at rest tend to stay at rest, unless acted upon by an unbalanced force. When we are riding in the carts, we are traveling at the same speed as the ride. However, as the cart experiences friction and negative work, we don't. Thus, the carts slow down, but we continue moving. That's why we need seatbelts and lap bars to ensure our safety and keep us situated in the ride safe and sound so that we don't fly out and die inevitably.